So now we will try to plot these different equations 1 to 4 and see what are the characteristic graph of a second order reaction. Okay, I will go a bit faster as these things are now routine, very routine now. So let me select equation 2 first. So this equation is of the form y is equal to m into x. So this equation is of the form y is equal to m into x, because this the entire quantity is considered as a variable. Similarly, this equation is also of the form y is equal to mx, whereas this equation is of the form y is equal to mx plus c. So let us select equation 2 first. Okay, in that case, okay, what would be the plot? It would be x divided by a into a minus x versus t. Okay, so if you plot x by a into a minus x versus t according to this equation 2, you should get a straight line passing through origin if it is a second order reaction, and you can easily see from equation 2 that the slope should give the rate constant of the reaction. On the other hand, if you plot, okay, only x by a minus x instead of x by a into a minus x, I take x by a minus x versus t. Then according to equation 3, the straight line should be passing through origin, but the slope of the straight line is slightly different from this slope. Okay, so in this case the slope is actually a into k, because a is a constant, k is a constant, so a into k is also a constant, so together it represents the slope of the reaction, so sorry, slope of the plot. So from this you can find out what is the rate constant. Rate constant is slope of the line divided by a. Or if we are concentrating on equation 4, what would you plot along y-axis and x-axis? You will take 1 by a minus x versus t, 1 by a minus x versus t. Since this equation 4 is of the form y is equal to mx plus c, okay, and you have a positive slope because k appears as positive here, k is term, k into t is positive, so you get a straight line with positive slope and non-zero intercept. Okay, you get a straight line not passing through origin and it is having a positive slope. Okay, so the intercept of this straight line is 1 divided by a, and the slope of the straight line gives rate constant k. So you have several ways to determine whether the reaction is second order. You can either plot x by a minus x versus t, or x by a minus x versus t, or 1 by a minus x versus t, and from any one of these you can easily find out whether the reaction follows second order, and if yes, you can easily find out what is the rate constant of the reaction. Now this is the reaction of the first type, where concentration of A is equal to concentration of B, that is concentration of both the reactants are same. What happens if the concentration of both the reactants are different? Okay, so we will only discuss the mathematical equation for this case, we will not go into the details. The second case is if the initial concentration of A and B are different, or you can write if initial concentration of the reactant is A and the initial concentration of reactant is B, and A is not equal to B. In this case, okay, following the mathematical procedure that I have explained for zeroth order reaction, it is easy easy to show that the rate constant for such a second order reaction is A is equal to 2.303 divided by time into A minus B, that is initial concentration of reactant A minus initial concentration of reactant B, into log of initial concentration B into A minus X, that is the concentration of the reactant at a time t, divided by A initial concentration of A into B minus X, that is the concentration of the reactant B at time t. So this is the expression for rate constant for a second order reaction when the initial concentration of the reactants are not same. Okay, the unit of rate constant of a second order reaction is same irrespective whether it follows the case 1 or case 2, where the initial concentration of reactants are same or reactant concentrations are different. The unit of rate constant, second order rate constant, is same. It is per mole dm cube per minute. Okay, so the unit of rate constant is same. So this is about the second order reaction. Okay, there is remember, there is not any such characteristic graph or plot for this particular case as we had for the first case. Okay, in the first case we had three different ways of plotting for a second order reaction, but for this case there is no graphical representation. Okay, therefore we will leave it here as such. Now let us generalize these things: zeroth order reaction, first order reaction, second order reaction. What would be the expression for a general nth order reaction? So general nth order of a reaction, but remember where n is a integer, we are only speaking reactions of integral order. So in such case, dx by dt, that is the rate of the reaction, is equal to rate rate constant into concentration of A at time t to the power n. Okay, where n is the order of the reaction, or you can also write it as k into A minus x to the power n, where A minus x is the concentration of the reactant at a time t. Okay, so this is the rate equation for a general nth order reaction. Okay, you can rearrange this equation and integrate, find out the integration constant, again make some rearrangement and find out an expression for rate constant. We do not need all those mathematical steps. Okay, we only require the final expression for rate constant, which is the rate constant of the nth order reaction is 1 by t, that is time, into n minus 1, where n is the order of the reaction, into 1 by A minus x to the power n minus 1 minus 1 divided by A to the power n minus 1. Okay, so this is the expression for rate constant for a general nth order of a reaction, and by substituting different integral values of n, you can obtain the expression for rate constant for different ordered reaction. So previous ನಾವೇನು zeroth order, first order, second order reactions ಎಲ್ಲ ಇಂಡಿವಿಜುವಲ್ ಆಗಿ ಡಿರೈವ್ ಮಾಡಿತ್ತು, ಆ ಫೈನಲ್ ಎಕ್ಸ್ಪ್ರೆಷನ್ಸ್ ಅನ್ನು ಇಲ್ಲಿ n is equal to 0, 2, 3, 4 ಎಲ್ಲ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿದರೆ you can immediately and easily obtain all those expressions. But remember, this equation is not applicable for n is equal to 1. Yakandre, if I substitute n is equal to 1 here, this n minus 1 becomes 0 and 1 by 0 is not defined. Therefore this equation holds good for all reactions, integral ordered reactions, except n is equal to 1. So if I substitute n is equal to 0 and make some rearrangement, okay, the same equation that I derived for 0th order reaction can be obtained from this also. Similarly, if I substitute n is equal to 2, okay, for I can obtain the expression that I had earlier derived for a second order reaction where the initial concentrations of the reactants are same. So if you remember this equation, general equation, you can reproduce equations for a particular order. What is the unit of K now? So if you look at the RHS, you have 1 by time, n minus 1 has no unit, okay, both are the same, the first term and the second term. So let me concentrate on this term. So you have unitless quantity divided by concentration to the power n minus 1. So the unit of K will be 1 by time unit, that is 1 by minute, into, this is unitless, okay, let me concentrate only on the first term, 1 by concentration, that is mole per dm cube to the power n minus 1. So if everything is taken to the numerator, it becomes mole per dm cube to the power n minus 1 becomes 1 minus n minute inverse, mole per dm cube to the power 1 minus n minute inverse. And from this, by substituting different values of n, you can reproduce or find out the unit of rate constants of 0th order, 2nd order, 3rd order reaction. So again, this is not applicable for n is equal to 1. So these are the general expressions for a nth order reaction. Now let us define and find out the characteristic of the reaction called as half-life of a reaction. So half-life of a reaction is a very important aspect related to chemical kinetics. Okay, one, it is a measure of how speed the reaction is taking place, whether it is a fast reaction or a slow reaction. To find out that, one of the ways is to measure what is called as half-life of a reaction. The other way half-life of a reaction is important is, if you determine or if you know what is the half-life of a reaction, it is possible to find out the order of the reaction, or it is possible to find out what is the rate constant of a reaction. Remember, in chemical kinetics, the two important physical quantities that we will be discussing and are of importance is order and rate constant. So one of the method to find out the order of the rate constant uses the method of measurement of half-life of a reaction. Okay, so let us first define what is half-life. We know that all the reactions do not proceed with the different rates, so different reactions generally have this different half-lives. Okay, so half-life is a characteristic of a particular reaction. So first we will define what is half-life and try to find out what are the characteristic features of 0th order, 1st order, 2nd order reaction with respect to this half-life. So half-life of the reaction is the time taken for the concentration of the reactant to reduce to half of its initial value. So I repeat, it is the time taken for the concentration of the reactant to reduce to half of its initial value, and it is represented by the symbol T half. Say for if you have a reaction A giving product, okay, and I will not speak in terms of concentration, I will speak in terms of molecules, okay, so that things looks very easy. So at T is equal to 0, at T is equal to 0, I have taken 10,000 molecules of A. 10,000 molecules of A. So as the reaction starts, okay, the reactant A, okay, will be converted to product. So concentration of A starts decreasing with the time, and at a particular time T is equal to, say for example, 8 minutes. What I observe is the concentration of A is 7,500 molecules, okay, in terms of molecules. Therefore, whether T is equal to 8 minutes, okay, 8 minutes represents half-life of this reaction. So T is equal to 8 minutes does not represent, okay, or it is not the half-life of this reaction, because what is half-life? It is the time taken for the concentration of the reactant to reduce to half of the initial value. So initial value here is 10,000, half of that is 5,000. So the time taken for half of the reactant to be consumed. So since the reaction has not since the concentration of the reactant has not reduced to half of its initial value, this is not the half-life. For example, at 20th minute, okay, I measured the concentration of the reactant, and the concentration of the reactant is 5,000. That is half of the initial value. So T is equal to 20 is nothing but the half-life of the reaction. So this is the half-life of the reaction, okay. Or the reaction will not stop here, right? It will further proceed, and after another 20 minutes, okay, I measure the concentration of the reactant. It is 2,500. So if I take this as the original value now, 5,000, it has reduced to half of that, 2,500. So this duration, okay, can also be considered as half-life of the reaction. Or you may consider the next duration, okay. Say for example at 60th minute, okay, I measure the concentration of A, and it is 1,250 again, which is half of the initial value. For measuring the half-life here, I should consider this as the initial value, so it is half. So this duration is also half-life of the reaction. So this is called as the first half-life, second half-life, third half-life of the reaction. And for simplicity, okay, here the first half-life, second half-life, third half-life all are one and the same, okay. T half is 20 minutes, second T half is also 20 minutes, third T half is also 20 minutes. Remember, this does not happen always, okay. For a particular set of reaction, first half-life, second half-life, third half-life will be same, but it is not so for all the reactions. Now I will only take the example of a zeroth order reaction, okay. How to find out half-life of a zeroth order reaction. Okay, I will take the example of first order reaction, okay. So by using the same procedure, it is possible to find out half-life of zeroth order, second order, or in general nth order reaction. So first let us take the example of a first order reaction, okay. The rate constant is K is equal to 2.303 divided by T into log of A by A minus X, okay, where T represents time, A is the initial concentration, A minus X is the concentration of the reactant at a particular time T. When the reaction reaches half-life stage, okay, at a T is equal to T half, so what would be the concentration of the reactant A minus X? Remember, what is T half? It is the time taken for the concentration of the reactant to reduce to half of the initial value. So concentration of the reactant remaining unreacted will be half of the initial value, that is A divided by 2. So if I have taken 10,000 molecules, how many molecules of reactants A are remaining unreacted? That is half of 10,000, that is 5,000. So A minus X will be equal to A by 2, and X, what is X? It is the concentration of the reactant which has already undergone reaction. Now out of 10,000 at T is equal to T half, 5,000 is remaining unreacted. What does it mean? The other 5,000 has already reacted. So the concentration of the reactant unreacted and the concentration of the reactant reacted will be same at T is equal to T half. So out of 10,000 molecules, 5,000 remains unreacted, 5,000 remains reacted. It is a half stage. So here A minus X is equal to A by 2, and therefore X should be also equal to A by 2. So remember this mathematical condition: at T is equal to T half, X is equal to A by 2, A minus X is also equal to A by 2. We do not require this X value here for a first order reaction, but you require this when you are dealing with zeroth order or a second order reaction. So let us substitute this condition in this equation. K is equal to 2.303 divided by T half into log of A divided by, what is A minus X at T half? It is A divided by 2. Okay, that is K is equal to 2.303 divided by T half into log 2, because A gets cancelled, and this 1 by 1 by 2, okay, is log 2. If you simplify this, it becomes K is equal to 0.693 divided by T half, or T half is equal to 0.693 divided by K. So half-life of the reaction is 0.693 divided by rate constant, and remember this equation is only applicable for a first order reaction. An important point that has to be remembered here is this half-life of the reaction does not depend on the initial concentration. So half-life does not depend on initial concentration A for a first order reaction. For a first order reaction. So this is one of the important salient characteristic feature of a first order reaction, that is half-life of a first order reaction does not depend on initial concentration of the reactant. What does it mean? I will explain you in this in the regular live class. Okay, remember this. I will ask you this as a question. Okay, what is the meaning of half-life of a first order reaction does not depend on initial concentration? Similarly, you can derive by using zeroth order reaction an expression for half-life of a zeroth order reaction. Okay. So for a zeroth order reaction, what is the expression for rate constant for a zeroth order reaction? K is equal to X divided by T. Now if I substitute the condition of half-life, that at T is equal to T half, what is X? X is equal to A by 2. So K becomes A divided by 2 divided by T half. That is K is equal to A divided by 2 into T half, which implies T half is equal to A divided by 2 into K. T half is equal to A divided by 2 into K. So this is an expression for half-life of a zeroth order reaction. Now look at this equation. How does half-life depend on initial concentration? Does it depend on concentration? Yes, it depends on the initial concentration. How it depends? T half of a zeroth order reaction is directly proportional to the initial concentration. So greater the initial concentration of the reactant, greater is the half-life of the reaction. So for a zeroth order reaction, half-life is directly proportional to the initial concentration of the reactant. On the other hand, okay, for a second order reaction, when concentration of A is equal to concentration of B. Remember, this is the first case when the initial concentrations of the reactants are same. In such case, the half-life of a second order reaction will be equal to 1 divided by A into K. So, for a second order reaction with the initial concentrations of the reactants are same, half-life of a second order reaction will be equal to 1 divided by A into K. And by looking at this equation, you can clearly see that the half-life of a second order reaction is inversely proportional to initial concentration of the reactant. So for a first order reaction, half-life was independent. For a zeroth order reaction, half-life was directly proportional to the initial concentration, whereas for a second order reaction, half-life is inversely proportional to initial concentration. So how half-life depends on the initial reactant concentration depends on the order of the reaction. So by understanding the relation between half-life and initial concentration, it is possible to find out the order of the reaction, because for different orders the relation between half-life and initial concentration is different and it is unique. It is for a particular reaction, it is unique. For a zeroth order reaction, half-life is always directly proportional to A. For a first order reaction, half-life is independent. For a second order reaction, half-life is inversely proportional to A, and these relations are true only for a particular reaction. There is no other reaction other than a first order reaction where half-life is independent of A. So half-life can be used, okay, for finding out the order of the reaction. How that mathematical details we will discuss in detail later. Now what is the expression for half-life for a general nth order reaction? And before that, I would like to ask you a question, and in my regular live class we will try to find out the answer. It is not possible to define half-life of a second order reaction if the initial concentrations of the reactants are different. Why? I repeat, if A is equal to B, if the initial concentration of the reactants are same, you have a half-life for a reaction. But you cannot have an half-life for a second order reaction if the initial concentrations of the reactants are different. Why? Okay, that is one question that we'll discuss. The other question we'll discuss is, or no, it is not a question, we'll discuss in detail the meaning of, okay, what do you mean by half-life does not depend on initial concentration of a first order reaction, or half-life is inversely proportional to initial concentration for a second order reaction, or half-life is directly proportional to initial concentration of a directly proportional to initial concentration for a zeroth order reaction. What is the exact meaning? Okay, we will discuss in our live class. So let us consider the nth order reaction. Okay, I will rewrite the expression for K. K is equal to 1 by T into n minus 1 into 1 by A minus x to the power n minus 1 minus 1 by A to the power n minus 1. So if I substitute the condition that at T is equal to T half, A minus x will be equal to A by 2. Okay, if I substitute this condition here and if I make some rearrangements, okay, I will obtain an equation for T half. The expression is T half is equal to 1 divided by K into n minus 1 into 2 to the power n minus 1 minus 1 divided by A to the power n minus 1. So this is the expression for half-life of a reaction following a nth order kinetics. Remember, this is only true if n is an integer. So half-life of an nth order reaction is 1 by k rate constant into n minus 1 into 2 to the power n minus 1 minus 1 divided by a to the power n minus 1. So for a reaction, k is a constant, and for a reaction, order is also fixed. So this is a constant. This numerator is also constant. So you can also write this as T half is inversely proportional to a to the power n minus 1. T half is inversely proportional to a to the power n minus 1, or you can also write it as T half is directly proportional to a to the power 1 minus n. Okay, T half is either inversely proportional to a to the power n minus 1, or T half is directly proportional to a to the power 1 minus n. So let us substitute n is equal to 0 here. Zeroth order reaction, T half is directly proportional to a. That is what we proved. Okay, if n is equal to 1, T half is directly proportional to a to the power 0. It means T half is independent of a. That is true for a first order reaction. If I substitute n is equal to 2, so T half is proportional to a to the power 1 minus 2, that is a to the power minus 1. Therefore T half is inversely proportional to initial concentration. So this is a general equation. By substituting different values of n, you can find out what is the relation between T half and initial concentration for different reactions, and we will reproduce the same thing that we discussed, okay, in detail for each reaction. And if I substitute different values of n here other than n is equal to 1, remember n is equal to 1 does not hold good here, because if n is equal to 1, this becomes indefinite. So this equation can be used to calculate an expression for half-life for a zeroth order reaction, second order reaction, or third order reaction, or any reactions where n is a integer other than 1. ಸೊ ಮೊದಲು ನಾನು ಏನೆಲ್ಲ ಎಕ್ಸ್ಪ್ರೆಷನ್ಸ್ ನಾನು ಬರೆದಿದ್ದೆ ಫಾರ್ ಹಾಫ್ ಲೈಫ್, ಆ ಎಲ್ಲ ಇಕ್ವೇಷನ್ಸನ್ನು ಈ ಮೆಥಡಲ್ಲಿ ಕೂಡ ರೀಪ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ಬೋದು ಬೈ ಸೆಟ್ಟಿಂಗ್ different values of n other than n is equal to 1. So half-life is an important characteristic of a reaction. Okay, half-life for some reactions will be very high, half-life for some reactions will be very low. So it is a characteristic of a reaction. And more importantly, how does half-life depend on the concentration of the reactant is the characteristic of the order of that reaction. Okay, what does it mean? If it is a zeroth order reaction, half-life is directly proportional to concentration of the reactant, or vice versa. If the half-life depends on the concentration, it means that it is a zeroth order reaction. If T half is independent of the initial concentration, it means that it is a first order reaction, and vice versa is also true. That is, if it is a first order reaction, T half is independent. Similarly, if T half is inversely proportional to initial concentration, it means it is a second order reaction, and reverse statement is also true. That is, if it is a second order reaction, T half is inversely proportional to A. So this T half is a very, very important physical quantity related to chemical kinetics of a reaction. So in these two videos, class 4 and class 5, okay, class 4 and class 5, we tried to concentrate on some mathematical aspects or the salient features or characteristics of zeroth order, first order, second order, and nth order reaction. In the next class, we will discuss the actual topic, that is reversible reactions and parallel reactions. So we will discuss the chemical kinetics of reversible and parallel reactions. Thank you.